Hi, welcome to this video, and in this video I'm going to answer some questions around really the teaching of STEM and in particular the monitoring of water quality. So I'm going to talk about a little bit about bacteria, a little bit about pesticides and quite a lot about heavy metals. Now what I'm going to do is I've got some hardware in front of me and I'm going to introduce that very quickly, very shortly I should say, and then come back to it. So there'll be quite a few things going on here, but let me just sort of go first of all to the next slide. What I'm going to do here is just show you that I've collected, in fact here it is, a water sample from one of my taps, because this is going to become relevant very shortly. So here's the tap water. You'll see me prepare a sample with that, and then I will go on and do the presentation, then come back at the end and get the results. So let me go here where I've got the word demo. So I've got a Sensi-All in front of me. Now the Sensi-All, I'm going to do a very particular demonstration now, which will be measuring the heavy metals in a water sample. So I'm going to take that off. This is one of our lead and copper sensors. I'm going to grab a fresh one. I'm going to put that on the device. Now the Sensi-All is kind of, the name is sort of suggests what it might be like, but actually using different QR codes, that was slightly out of shot, but using QR codes I can actually go into different modalities. So at the moment my app says lead and copper. Okay, lead and copper. Now what I'll do is I'm going to Bluetooth connect to that device, which I've now done. I'll put the word demo into here. This is so I can find the data later on, because I'm going to do a live demonstration tap water 101. That'll make it easier. Now I'm going to prepare the sample. So I want you to kind of imagine that I'm in some sort of rural community. I don't want to wait 6 weeks for my test results to come back. So I'm going to prepare my sample now. So I'll take 1 volume or 100 microliters of tap water, which I have done. I'll put them into a little tube. I take 100 microliters of buffer. This is because you can't always know the ionic concentration, the pH of things like of tap water. So I've just put 1 volume of tap water with 1 volume of buffer. I'll just give it a quick shake. But the nice thing about those two liquids is obviously they're miscible, so they just go together nice and quickly. Now what I'm going to do is I'm going to take 50 microliters of this sample. So 50 microliters. Previously, by the way, I was doing 100 microliters plus 100 microliters when I was preparing that sample. Right, now I'll put it onto the... now this is tap water, by the way, from my house. So wish me luck, because I'm going to be testing for copper and lead. All right, put the sample on like that. Now I'll take the app and I'll go continue. Now you saw me do a 1:2 dilution, so I'm just going to choose the number 2 here, start, and off it goes. So nothing super exciting there. I will leave that alone now, running in the background, and I'll go back to my, I want to say slides, but it's not, but I might as well use the word slides. Right, so I'm going to, we started that off, so let's just get back to the questions. So water testing is typically managed by government agencies, and I'll address that in a minute. It's because really the kind of most used instrument is an ICP-MS, an inductive coupled plasma mass spectrometer. This is this is a $250,000 instrument. Many students, and I agree with this statement, and many people are very interested in kind of citizen science. This idea that people are sort of taking ownership on the water quality or some other aspect of the environment by doing testing, and this is what's happening in healthcare systems as well, that you decentralize test. So that's what I'm doing at the moment. I'm decentralizing test. I'm actually able to take a sample of my water, put it on this instrument, and I'm analyzing in particular copper and lead, and we'll get back to that shortly. So most kits are doing heavy metal detection. That's true. That's what I'm doing at the moment. The students in this particular inquiry may want to develop a system for bacteria and salmonella. So the reason we're doing heavy metal is it's actually slightly easier than trying to do E. coli and salmonella. These are quite difficult sensors and assays to develop. It's not something that it's something that we do on paid programs, but developing a salmonella and E. coli sensor is actually quite tough. You've actually got this strange thing because with E. coli, for example, I know a fair amount of, you've got lots of, I want to say species of E. coli. So you kind of want both a sensor that's specific to E. coli, but then E. coli itself is quite a broad population of different E. coli. So it's actually quite a tough sensor to develop. I would possibly argue that salmonella is the same thing. We are able to do heavy metals, at least in this test now. I'm going to do lead and copper. We just haven't expanded onto arsenic and mercury. They're also interested in PFA. Now, lead, by the way, has got, in the USA, maybe depending on states, but it's about 4 or 5 parts per billion is the kind of lawful limit. And with copper, it's more like 1 or 2 ppm, so 3 orders of magnitude more. And when it comes to forever chemicals, it's parts per trillion. So it's a really hard thing to detect, parts per trillion. So that's why I'm sort of saying, I'm just commenting upon this really and saying, some of these things are easy, some of them things are much tougher. It's nice that the students discovered our website. So, we do contract development for pesticides, fertilizers for definites. Heavy metals is something that we just sell. And we also do contract manufacturing or development also for microbial. But not all of these sensors are available. What I'm showing at the moment is available. And I'll also talk about sometimes what's stopping the students progressing is maybe an education in the science of electroanalytical chemistry, which I will touch upon as well. Specific details were not found. Well, I'm doing a live demonstration now, so hopefully that will help you. So the particular instrument I'm using at the moment is the Sensi-All. I'm happen to using it in a lead, or rather detecting lead and copper. And in fact, it's just coming to the end here. So let me just go to here. So we've got about 5 seconds left on this. So now it's going through to the analysis. So it was preparing the sample. Now it's going to do the analysis, and then we'll get a result. Let's have a quick look. I probably just see a bit of copper just coming there now. It's a tiny little bump, but that will probably be the copper. I probably have no lead, and I probably have some copper. So let that just process. So that will process. There we go. So the lead, thankfully, is low. So that means it's really below 4 ppb in my house, which is good. The copper is detectable, but the limit for copper in the UK, I think, is about I think it's 2 parts per million. So you can see that I've got essentially 628 parts per billion, so 0.628. So I was expecting the copper. Now that's because, in fact, I'm in basically I have copper pipes. And I'm in an upstairs bathroom, or near upstairs bathroom. So that means that I've picked up quite a lot of copper in my pipes. Let's just go along a little bit more. Just out of interest, the instrument itself is about €1,700, which may translate to about $1,700. I know we're living in interesting times, so there may be some extra taxes on those kind of things, which is, so we've got the instrument, but then there's the kits themselves, and then the price goes up. So they're looking for compatibility with microcontrollers. So as you can see that we have a sort of turnkey solution here. But what might be interesting, first of all, just to comment on lead and copper. The incumbent device, by the way, is, a daisy. I realized that I wasn't sharing my screen, so I'll just share my screen. We do have a kind of complete solution, but there's also an educational version of this, which might be kind of useful for the students. But just to say, this is the incumbent device, an ICP-MS. it's super expensive. It needs lots of people. It takes a long time. It costs a lot to get the sample. You have to send that sample back to the lab. Processing that sample for ICP-MS is really expensive. You need highly trained technicians to run it. You've got quite an expensive facility. So there's a real advantage in shrinking lab-based procedures down to point of care, or point of need, which is what we've done. Now, I'm going to put a link as well to kind of an education system, because what's possibly not so much holding students back, but actually is how well do students understand electroanalytical chemistry. Before you can jump onto Salmonella, E. coli, microcontrollers, etc., you possibly have to have a good grounding in electroanalytical chemistry. And then electroanalytical chemistry is really the science behind every glucose reading. People are type 1 diabetics or type 2 diabetics, they're pricking their fingers, they're testing their blood. That's all based on electroanalytical science. What I just did is also based on electroanalytical science. So what I will do is say, if you've got any questions regarding STEM and technologies of ZP that can help in STEM education, then please don't hesitate to reach out to us. Okay, thanks very much.